Welcome to this video on other applications of Kirchhoff's loop rule. The primary objective of this video is to take a look at situations where it's not as obvious as to what a certain circuit element is doing in terms of providing or using energy from the circuit. And these images that I'll be using here are from the OpenText BC website. I have a link in the description below to this awesome open source text. They have many different texts available, and the physics ones are very, very helpful. So check that out. Let's take a look at this single loop up here. Now this single loop, all of these circuit elements share the same current. They're connected in series with one another, and I know this because there are no junctions between any of the circuit elements. Now, if I'm going to track my way around this circuit, working from, let's pick this EMF 1 over here, or voltage 1, as I move through this circuit, I would say obviously that this battery might be providing energy to the circuit in the form of the chemical energy from the inside of the battery. We know that resistors would use up, so to speak, some energy or dissipate energy as heat. And then I get to this over here and I see a weird situation. I'm hitting the positive terminal of this second battery, and as I work my way through it, what's happening here? Is this adding or removing energy from the system? If you think of your common experience, when you put two batteries in a device, you usually need to put them positive to negative ends touching so that you have a direction where you'll have a net positive end and a net negative end of the battery. Here, however, the two positive ends are facing one another, and so this presents an interesting problem, so to speak, for tracking the energy or the voltage increase or decrease. Now remember, voltage is not energy itself, but it is directly proportional, and so we can use that to help us track whether the voltage is increasing or energy is increasing or decreasing for the charges that are moving through the circuit. So what I'm going to do is, my rule of thumb is to always start at the positive terminal or the negative terminal of the highest voltage power supply. And so what I would say is, as I move through this battery over here, there'd be an increase in potential for any little charge that travels through. So I would have an increase here, so I'm going to put a plus, and when I get to this resistor and I move through it, I would have a decrease in potential. Now I get to this battery. Let's come back to it. We'll get to this point here, we'll have another decrease, and we'll be back to 0. Now if I think about it, as I get to this point over here, I'm going from a high potential point to a low potential point. That means that the potential is dropping across this battery as I move through. So this is actually going to be a negative. Another way I could track this would be to do the following. So let's write out a Kirchhoff statement for this circle or this loop. Over here I'm going to start with a positive increase. So this is going to be delta V 1. Now I have a drop minus delta V, and I guess instead of putting this as delta V, I'll change it to the EMF notation just so I can distinguish between these two. Over here I have said that should be a drop, and we'll take a look at that here, and I'm going to do again, sorry, an EMF notation. And then here I have another drop of delta V2, and that equals 0. Now, if I were to actually calculate this minus this minus this, I would see that I haven't hit 0, and if I had added this EMF2, I would be at something other than 0. So that would imply that energy had come into the circuit in another way that wouldn't necessarily be what we actually see in this situation. So this is another way that we can track that the energy is dropping, is for all of this to add up to 0 and this to be 12, you have to subtract that term. So what I'll do next then is go ahead and plug these values in. This would be 24 minus, now what I'm going to do is substitute in I times R for the delta V for that drop, and I can do this because the resistance is independent of the current or the voltage and it's constant. So I'll do I times 10 kilo ohms, just remember that's a kilo ohm, not a ohm, minus 12 minus I times 30 kilo ohms equals 0. So combining constant terms here, I have 12 minus, and then I have 10I minus 30I equals 0. I can combine like terms again, 12, so I have negative 10 plus negative 30, which would give me negative 40I equals 0. And then I can set this as 12 equals 40I, divide by 40, keeping in mind here that this is a kilo ohm, and I would have a value for my current of 0.0003 amps. And you could write that in scientific notation if you so desired. So we see here that I have a current that's the same throughout this process. Now, it's important to note that what's really happening here is that you're actually recharging this battery. So the chemical process that would naturally occur when you attached two wires to the ends of the battery and connected them to something would be that the chemical reaction would move charge in this direction, right, providing energy to the charge from the chemical storage. Now, when you go in this direction, what's actually happening is that you're pushing the chemical reaction in the opposite direction, and that is kind of conventionally called recharging the battery, so to speak. Now, if you recharge a battery, you're actually re-energizing it. You're running a chemical process in the opposite direction to restore, if you will, the chemical energy in the battery that can be used again later. So in other words, this would be like plugging in a battery into an outlet in order to quote unquote recharge the battery. So it's using up energy in this case. And so you can see that that is what would happen. Here is the set of rules for how to keep track of whether you have a potential increase or decrease. What I always think about is that if I'm going from the high to the low terminal on the internal battery, that's a drop in potential. And if I'm going from the low to the high potential, that's an increase in potential. So that's fairly easy to remember. The one that's just a little bit maybe more confusing, but it's just conventional here, is based on the direction of the current. If I'm traveling in the same direction as the current, I would have a drop in potential over a resistor, which is the common point that makes sense because a resistor heats up and that dissipates the heat. If I go in the opposite direction of travel here with a resistor against the current, I would actually have an increase in potential. Now, that doesn't mean that the potential is actually increasing as I work through the circuit in reality. What this is saying is, conventionally speaking, based on the direction that you're traveling, in order to show that energy is conserved, you're going to be subtracting regions where the voltage in reality is actually adding potential to the circuit. And so in order to keep the convention that you're using on your own choice, you actually have to add potential for each of these so that everything will add to 0 at the end. We'll take a look at that in a subsequent video, but just keep in mind for right now that when you decide on the direction of the current, if you travel in the same direction as you write out your Kirchhoff statement, you need to keep in mind these conventions. Whether you're going in the direction through a certain circuit element will identify whether you need to add or subtract. It doesn't matter which direction you go, it just matters that you keep the correct sign convention for that particular direction so that you don't end up adding energy to the circuit that isn't actually there or taking energy away. In the next video, we're going to take a look at multi-loop circuits like this one over here. where it's a little bit more complex because there's not only one current like there is here. In this situation, we're going to learn a really cool technique that's a little tedious, but very cool in solving for multiple unknown currents in a circuit such as this. We'll take a look at that in the next video.